Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy to understand videos. My name is John, lead tutor for physics and mathematics, and in today's video we're going to be exploring vector algebra because vectors are super important for physics. They're like the language of physics, so let's just get started. So first, before jumping into a lot of math, we just need to understand what this vector thing is to begin with. And to start off, just think of every number you've been working with up to this point. So 0, 8, -3, pi, or really any variable or equation for that matter. All those are called scalars, and it basically just means one number. A vector is like a building off a scalar. It's just a list of numbers. You see to the right here that I have this bracket notation, which we use for vectors. It has two elements in it, x and y. You can actually get pretty creative and graphically show vectors. If we have this example of vector 2, 4 here, you see you can actually represent it on the xy graph. All you have to do is just go over 2 and up 4. We assume that the first one's always x and the second one's always y, and we're basically able to map every vector we want to just using this. It's a visual tool. It helps you understand it better. We can do the same thing with 3D. It's just adding that extra z component on. So we'll have a list of three numbers instead of two. You can also represent this with the 3D graph. You go 2 across the x direction, 5 across the y, and 1 across the z. And there's your vector. In fact, vectors don't need to have a limit, the number of numbers they have. It just needs to be one list. So yeah, vectors can be more than just 2 or 3 numbers, but our visual stuff stops at 3 because of 3D space. So far, I've been using these brackets. You're not always going to see those. Brackets are nice because they just order the numbers. I'm picking this 8, -4, 1, just an example. There's going to be other ways you'll see it. For example, you'll see these arrows, which just rearrange some terms. You'll see this I, J, and K, which is just the X, Y, Z. These are used a lot in engineering. The second example over here is just to show you don't have to add that one K. You can just leave it as K and people will know what you're talking about. And then this last example is to show that it's x, y, and z. So I corresponds to x, and if you wanted to, you can have these vector hats. I don't know, I like them. So on to the more interesting stuff. Vectors aren't just to be looked at to look nice. They are an actual piece of math. So just adding and subtracting vectors, it's pretty straightforward, just like regular addition subtraction. You add up each element, so 1 and 3 should give you 4, -2 and 3 should give you 1. But adding and subtracting vectors gets interesting, especially once you do these arrows. So you see, I actually have this exact same problem. This 1, -2 is this blue arrow here, and this 3, 3 is this green arrow. If you want to add visually, it is called the tail to tip method. And what you do is you take this green arrow and you shift it down like I have in this picture, down to the tip of that blue arrow. So the blue arrow will end and the green arrow will begin. Your resulting vector, that 4, 1 we just solved for, this orange one, will go from the original tail to the green's tip. And that's your actual new vector. Just a nice visual proof of what we're doing here. Subtraction is the same thing, you just subtract them instead of add them. So this leads to a pretty good segue into components of vectors. Every vector is just a bunch of different vectors added to it together. So imagine it like this. Imagine like a ball in a stream. There's two currents pushing on it. One is pushing in the Vx direction, the other is pushing on the Vy direction. That ball's trajectory is going to be that V vector right there. It's kind of like we're adding this Vx and Vy tail to tip like. But take a look at this. This creates a triangle, right? With V as the hypotenuse. So if you know any trigonometry, you're able to explain the horizontal and vertical positions in terms of the magnitude of the vector times the trig function that it's related to. But a lot of mistakes I see students make is cosine is always x and sine is always y. 9 times out of 10 that's going to be the case, but that's only because you're measuring this angle right here. If I had to take a look at this top angle right here, those would flip. So x would be sine and y would be cosine. It is nomenclature about sine and cosine, the fact it's adjacent opposite, not this leg and that leg, so you got to be careful of it. So components lead us to the length of the vector. We just call this the magnitude. I'm going to take this example 3, -4 for instance. And just like the last photo, The components of vectors create a right triangle with whatever vector you're looking at. So it's quite literally just doing Pythagorean's theorem to find out how long it is. And doing the math, we're going to get that this vector over here is 5 units long. It's a 3, 4, 5 triangle. Good example of what I'm trying to show here. So I love unit vectors. Quite literally, they are just a vector whose length or magnitude is 1 that points in whatever direction you want to look at. They're really nice because you don't need to show it as this x plus this y. It's just no, it's the magnitude times its unit vector. How you find the unit vector is take whatever vector you're looking at and divide it by its magnitude. So let's flip the previous example and make it positive 3, 4. Let's try to find this vector's unit vector. You do the 3x plus 4y, and you're going to divide each term by 5. So in the end, we should get 3/5 plus 4/5. Just to check, you'll Pythagorean add them together, and you'll get 1 for your answer. Every unit vector has a length of 1 after all. The x, y, and z system that you all are familiar with, but never really went too much into explaining. That is just 3 unit vectors, all perpendicular with each other. The I, j, and k vectors are used to describe x, y, z units, and we call that the Cartesian coordinate system. So the last little segment of this topic is just going to be more math stuff. We're going to get into 2 types of multiplication and then some laws and properties, and we'll call it good. First being the dot product. The dot product is when you want to multiply 2 numbers together to get a single scalar value. That's that single number. Just taking a look at this quick example, 2, 4 times 3, 8. It's clear to see with dot product when it comes with vectors, you multiply element-wise and then you add everything together. So it's going to be -6 plus 32 gives you 26. If you know the magnitudes and you know the angle between each vector, you can also use that to figure out the dot product. It's just the magnitude of both vectors times the cosine of the theta between them. When it gets to 3D problems, finding that theta will be really hard, but for 2D it's not too bad. But I'll leave it as an exercise to the viewer to check this second equation. The cross product, on the other hand, is when you want to multiply 2 vectors together to get another vector. And since this is Phys 1 and it's assumed y'all haven't taken linear algebra yet, I don't want to bore y'all with how to take a determinant just to find out how to do this thing, so I actually came up with a shorthand way to find the cross product of 2 vectors. I'm going to need to go out of my presentation, but since you know you're going to multiply 2 vectors together to get another vector, what you do is for the first element, you cover the first 2, then you want to take this diagonal, -3 -4, and subtract that diagonal, 10 -7. That's for the first one. For the second one, you just cover that second row. You do the same diagonal, 2 times -4, -3 times 7, and then you do the same thing for the last one. So you're crossing out the row that you want to find your answer for, and you're taking the cross subtractions of the other rows. And if you see through the math, you'll get this answer. Just like dot product has a cosine with it, cross product has a sine with it, and it's still the same magnitudes. So we're going to finish off with some properties. First one being this commutative property between a scalar and a vector. All this says is if you have a scalar like 3 in this example, it really doesn't matter where you put it. You can put it before or after the vector, and it's still going to equal the same thing. And it's the same as scaling up each element by 3, so you'll get 6, -9 for this answer. Second one is the distributive property for scalars. So we're just adding these 2 vectors, and it's the same as just scaling each vector and then adding them separately. And then last we have the additive commutative property. So it's just like this one up top being multiplied, except now you just add the 2 vectors, and it doesn't matter which order you add them in, it's still going to give you the same answer. I've put some further readings if that's your sort of thing. I highly recommend this first and third link. These are also TutorTubes made by our channel from lead tutors. Highly recommend them, but otherwise that's going to do it for this TutorTube. Thank you for watching. I hope you enjoyed it. Please subscribe to our channel if you want to see more videos about physics. Please check out the links in the description for more information about the Learning Center. Make sure to follow us on our social media. Thank you, and we'll see you next time. Hello and welcome to TutorTube.